So, hello everyone. This is Siri Maros from Chemspace, and it's my great pleasure to have you here at our another exciting webinar. So, before we begin, just a few questions I would like to ask you, and hopefully you can hear and see me now. So, if yes, then could you please type something here, either in questions or in the chat box. Okay, great. Thank you. Few rules that we typically have for all the webinars. First rule is that you will be muted during all the webinar, and you can ask your questions through the question box. Second rule is that webinar will be recorded, and you will receive the link to the recorded version once the webinar is finished. The third rule is that if you would like to the announcement, if you would like to know more about the upcoming webinars hosted by Campspace, you can always follow us through social networks or through the news on our webpage. Just to remind you who we are and what we're doing. So Chemspace, that's a platform for small molecules where you can log in and buy them from. And the idea for Chemspace is to create the environment for researchers to look for the offer from different vendors and order the compounds in the way that it's a single PO procedure. The Chemspace catalog is available online as well as through the punch-out integration with the ERP applications such as SAP, Coupa, Ariba. With this, you will have access to all the Chemspace features, and you will receive the simplified purchasing process. We have already successfully launched this at 5 locations. And under the access, I mean that you can have ability to search for over 400,000 in-stock building blocks, over 6 million in-stock screening compounds, and billions and billions of make-on-demand analogs to in-stock building blocks and screening compounds. And if at some point you're not able to locate the molecule of interest, we can always help you using different sourcing and procurement models. The search on Chemspace is fast and allows you to do all classical ways that are used by chemists, as well as you can do the text search through CAS, MFCD, etc. And you can have your files imported, such as in a format of SD, or a list of smiles or items IDs. And through Chemspace, you can have access to the largest synthetically available chemical space, and that's basically enamine real space. The search is fast, especially if you're talking about the size of the space you can access, and that's over 17 billion items. And you just need just a minute or so to get the results from this huge chemical space. We also enabled a search of tool compounds, so you can use the name, trade name, synonym to look for the molecule you might use in your assay. And that's basically how you can do this. For example, you want to have Gleevec, and here you go, you can type it, and find the molecule and the vendors that offer it to you. We have tried to put many products in our portfolio, and one of them is actually a set of the products related to DNA-encoded libraries and the actual libraries. And those includes the building blocks that we collected, assuming that they can be used to build the DELs, as well as the product that been developed by Hijin, that's called OpenDEL, that allows you to really screen billions of molecules in just a while. And I brought this topic of DELs because today we have really, really interesting talk, and that will be provided by Xiaojie Liu. He's a principal investigator at Shanghai Institute of Materia Medica of the Chinese Academy of Sciences. So a few words about our speaker. So Xiaojie received his PhD in synthetic organic chemistry from Brandeis University. In 2010, he joined GSK encoded library technology department, and since 2017 he's joined the Shanghai Institute. So today Xiaojie will tell us more about DNA-encoded libraries and the technology that has been enabled by him and his group. With that, I would like to pass word to Xiaojie and encourage you to listen to our webinar and talk. Xiaojie?
Hi.
Yeah.
So should I share my?
Yeah. Yes.
Okay, I will share my screen now. Yeah. Yeah. Can you see my slide now?
Yes.
Okay. So I will just. Okay. Yeah. Can you see the first screen now?
Yes.
Okay. Yeah. Many thanks for the introduction, and today I'm going to talk a little about the DEL technology, which is about the research work which has been done at my research group, and I will also talk a little bit about the historic development about this DEL technology, especially on the recent rounds on DNA compatible chemistry reaction development, and then later I will also the next part will talk about a little about the intelligent. There is how the artificial intelligence could integrate with the DEL technology to speed up the small molecule drug discovery. And just a little of historical development about this, they are inspired by the visual display and the selected technology professor Richard Lindner and Brenner. They have come up with this concept with using the DNA as barcode to encode the chemistry library. And actually they brought this concept in 1992. Actually in 1993 they have already done some work, and actually there are two groups, and one is in FMAX, another is at the Professor Brenner's group and the Linder's group at the Scripps. And they have demonstrated that they could use the bead there to synthesize the tetramer peptide, and they have achieved the full concept and on this company. But unfortunately, because at that time the sequence is very expensive and nobody actually really to realize its significance until 2001. Professor David Liu has come up with this DNA template synthesis, and that is basically you can take advantage to using the proximity to bring the two reagents to close together to have a good action. And the original design is very elegant. They could enable the evolution. But the problem is like you always need to couple the reagent with the oligos, and this makes the library production very complicated, and it's not easy for the bigger library synthesis. So later new revolution come up with the idea to just use the single stranded DNA, use the straight link to the DNA coding, and but you can use the older style, the Comicat, just add the large reagent to increase the reactivity to solve this reactivity issue. And they could come up with the single stranded DNA construction. And then later, Professor Harvey also bring up the future to using the making one of the slides basically immobilized, and then you can basically take this advantage about the older chemical and making the solution can come into the solid phase, and they can come up with this idea for the DNA multi-phase. They can also do a nimble evolution. And also at the same time, my former colleagues and previously the research was created by the GSK and just in 2003 to 2004, they come up with this idea to have this band with this one terminal base they are already fixed by the double-stranded DNA. For example, in the left hand they could fix it, and on the right hand, basically you can do the using the T4 DNA like to do the decoding. And although this kind of design they couldn't do the evolution, but later after 2005, that's NGS has come up with it. So this could really save this technology and could speed up the sequencing. And this design later becomes quite powerful and in 2007 just quite a princess. And also I want to mention that there are also several types of their construction strategy, especially Professor Derineri have come up with this ESAC strategy, quite efficient fragment identification, and several years later, and Vibergen, they also have this user actor to make this type of DNA template library, and also Professor Xiaojie at the University of Hong Kong also developed this one universal template to make this DNA template libraries. Due to time, I don't have time to spend very detail on this technology. But in summary, they are although we all these technology are called there, but they are actually different versions of this. And here I just gave you a quick summary about it. And actually you can see, and more and more people, more and more groups are willing to using this original pieces and just design for their construction. The main reason is because of this type of head pieces. They are quite stable and they could tolerate the different chemical reaction conditions. And it looks like quite complete. Actually, it's quite simple. Just the DNA part could do the animatic coding using the T4 ligase and the chemistry, but this link goes through different type of chemical reactions and just go through this simple simple strategy. Just goes through the aromatic ligation and the chemical reactions. It's pretty quite efficient to make the 3 cycle average. And after you get this average and with this their pool, and you can go through the affinity selection, which is quite common in the big display for the antibody discovery. Basically, like you can immobilize the protein and just incubate with the library, and after you can after incubate you can use water to wash to remove the unbound library and the bound library. After you do the heat evolution, you can do the PCR and the sequence, and from the sequence data you can analyze the potential vendors and using these things as a traditional organic compound. Then you can use biochemistry and biophysics assay to confirm this activity. For example, this electrokinase case, which we have very well documented in the literature, and it comes from the very big and actually the third size is on 7.7 billion, but the feature is quite obvious. Basically, this building block 2 usually is quite dominant, and just combined with one of these building block up 2 steps, the chemistry is quickly easy to get this compound, and the initial hit actually is quite potent. Just go through a very simple Medica optimization. You can just go to find the preclinical candidate in it has gone into the phase 2 clinical study by the GSK. And it also has several other hits come from the DEL actually has significantly impacted. For example, this platform. The impact also actually is the original the hit compound from the GSK later was licensed to the padlock, and the padlock was acquired by the BMS actually. So you can see this technology that has a lot of commercial values, although there's currently no drugs has already funded by the DEL in the market. And this is another case funded by the GSK for the SH approach, and there was also quite successful to identify the hit compound and also quickly move to the clinical study. So let's go back to look at this the hit just a bit different as this response case we could clearly see from its data. It's quite obvious to identify this BB2. They have a whole frame and it's just all belongs to this BB2 building block, and they have different lines, and one of the lines is building block 3, this building block, and you just need to combine the building block 2 and building 3 together, and you can just get the hit compounds. Which means like although this is coming from a 3-cycle laboratory, but you can truncate the compound to make the high quality hits. But if we look at the papers in the literature, actually we can find a lot of hits recorded by they are now actually they have more than two fragments, and actually the truncated hit as this yellow one actually is not many. And that's because like some majority of the time it's not easy to do the truncation unless you have enough SAR, just like the phone case, and then you can do this. And so, but in order to have enough information about SAR, you really couldn't make to use the bigger libraries. As actually my former colleague Alex says now is at the Xiaojie and the publication, and he published here has clearly showed that it's better not to make the library, and actually it's not. It's better to have the library size less than 100 million. Actually, that's needed for their community, and more people are realizing it's better to use a high quality small size library to have the better quality of the selection data to have better data. And let's take a look at what you can get after you've done their selection. And this is the typical cubic you could clearly see. And in most of the case, what you will see just some scattered point, although some of the spots may have very high copies. And then sometimes you can see different obvious lines to give you some SAR information. Therefore, you want to see just like a report case like this BD with a building block dominating like a plane. Then you can are quite sure and this BD is going to be reached. And then sometimes you can also see a lot of lines they have interact with each other. So this basically gives you all kinds of different their selection output. What you want is like you could have enough SAR information for you to make the better decisions, to make to have the confirm the hits, and definitely you want the situations or like the wrong case, but definitely that's not the case at all. And the importance is you could have the better data and the ability to identify which compounds to follow up. So that's like some kind of like a very important factor for this technology. If the selection didn't work, the important thing for this technology is first your library should have you show the diversity, and basically that you didn't have the true vendors in your library pool. The second important thing is like you do have the good data analysis method to find the active hit from so many compounds in the mixture. So today I will basically talk about this, like one of the important things to increase the diversity basically is how to develop the novel or DNA compatible chemical reactions to expand the library diversity. And I will just give you a little brief overview of our current situation, and also talk about some of the progress especially very recently, how far and about basically the on-DNA reaction actually can do for especially for some novel on-DNA reactions. And this is basically a summary about the statistics about the published papers about the on-DNA incompatible reactions in the recent years. But you can see that at the beginning, like in 2015, there is only a couple publications, but after in 2020, there are almost to the 25 publications. And you can see more and more industry company and academic institutions are willing to publish this on the reactions. So actually, what is very good for this technology development. And for example, in 2018 to 2019, you could see for different type of on-the chemical reactions, and a lot of institutions such as not only the Pfizer GSK companies, and also like Harvard University and the Scripps, and they have the big guys in the synthetic organic chemistry. They are willing to doing research work on the incompatible reactions and have a couple of publications. So next, I will just talk about some of the work that have been done in my research group, and also have some of the excellent work done in the field, and to really especially this recent years, a lot of efforts have been put in this field to advance the DNA compatible reaction. So this is one of the examples which we have done in my research group. We take advantage of this very efficient scenario reaction. Basically, you can do the nucleophilic addition to with the ammonium salt, and actually we can do all kinds of different nucleophiles. The reason we are quite interested about this reaction is basically routinely we can use this is a pyrimidine scaffold, this trichloride scaffold to have a couple main addition reactions to make this 2,4,6 trisubstituted pyrimidines. And this we want to have some new basically new DNA linking part. Especially we want to use this lower Campspace. And so that's reason we synthesize this scaffold. And in this case, we can take advantage of this electrical withdrawing property of this ammonium salt, and in this way, the addition to the fully happened at the 2 position, and we can left this 4 position and 5 position with one step to do the SNAR to substitute this ammonium salt, and later we can do the coupling. And by this way, we can have a library they can both at the 4 and 5 position, we could have all kinds of diversity, and they can close together to really to show the power of the combination. And just using this strategy, we have seen that a very small library, especially its library size is just 10,000, but it's quite efficient. As you can see, we just using the BRD4 as a target to test, and you can see some of the only compound has already shown very good activities. And also, it's quite easy for us to expand this 2-cycle library to a 3-cycle library to make the library size around 100 million. And that could ensure you have the full diversity, and you can apply more building blocks to synthesize this diverse library. And also we can using the traditional methods as a tool to do all kinds of cross-coupling reactions. And one of the reactions we have done is to doing the hack reactions. And we also have done the stage activation reaction, because the recent 10 years stage activation reaction has a lot of publications. And taking advantage of this two new novel companies, we have designed and synthesized with pyrimidine-based libraries, and we can do this parallel library synthesis specifically at the cycle 3. They can be different, and both the hack reaction and the stage activation reaction could be used for this type of libraries, and we can compare really to see like what is the difference. We hypothesize this type of library could be, especially for the acid group left there, they could have some interactions with some supporting chemistry. And the previous work we have done is for the SP2 has this feature activation at Professor Jing Tong Yu and the Scripps research group. The Scripps they have done to using this SP3 and using their own chemistry, and they have elegantly demonstrated actually this SP3 stage activation could be happened with the own DNA, and they have designed this type of incompatible synthetic route to achieve the successful collaboration there. And we are really looking forward to see the library have come up using their novel chemistry to find some very interesting hit compounds. And besides the stage activation, actually the professor Schreiber at Harvard University, actually recent 2 or 3 years, he has also applied his source concept for the only chemistry reaction development. And this is one example they have using developed their novel only chemistry to make the complex molecule with more clear centers. And they have also of DNA synthesized the different serial isomers and linked with DNA to make 100,000 libraries. And the Professor Schreiber specifically thinks the small library could give the high quality of selection data, and they have demonstrated this type of libraries could find very interesting hits for different protein targets. And we are also interested about this type of source concept. So then we really want to develop the novel DNA compatible reactions to increase the diversity. That's why we have developed this strategy to think that different type of the unsaturated alpha beta alpha beta unsaturated ketones and use it as an intermediate. And we have designed and synthesized all kinds of different heterocycles, both as the aromatic and the saturated heterocycle with 5 and 6 membranes. And we believe this type of diverse rings combined with those concepts could find some interesting cases for many protein targets. And specifically, we have using the Austin scaffold as example to apply the source concept for the different type of the focus of single libraries. And the scaffold, we not only developed some novel OD chemistry to synthesize this type of spiral of spindles, we also using the traditional organic synthesis to synthesize the scaffolds. And finally, we have build these three new single libraries and with several protein targets. And finally, we have demonstrated that this diverse range of single libraries could find interesting hits for many protein targets. And we have also applied this intermolecular S-allylation coupled reaction for the microcycle library synthesis. And this is work using micro collaboration with Professor Thompson at the Medica University. And his group has developed this in-solution chemistry, and we have successfully applied this chemistry for the DNA compatible conditions. And it works quite well. And based on this novel chemistry, we have designed 8 three cycles microcycle libraries and applied for the P300 protein selection. And we identified the compounds and do the oxidation information, and we found actually the microcycle is important for the activity. And we think that the linear version of the compound actually and the compound has no activity at all. But the sequence one can give you the microgram, and which could be as a hint for the further Medicam optimization. And we with this those concept, we are also quite interested. We try to develop some novel using different ODA chemical reactions to develop the common intermediate, especially as the saturated heterocycles. So based on this, we have collaborated with the Chemspace, and we have developed this the separation just started with a very simple amino acid. We can cyclize this to form this saturated cycle ketones. And using this ketone, we can, as a starting material, we can make a different type of the aromatic and saturated heterocycles. And this reaction actually is quite efficient, and we can use it to make all kinds of different heterocycles. And currently, we have made several libraries based on this novel transformation. And all of this has this reactions we try to you apply the source concept to the different type of the heterocycle construction to expand the chemical diversity of the cell library. And another important field in this field is more and more novel chemistry, especially very recently, some radical chemistry and photochemistry has been widely advanced in the traditional synthetic chemistry. And unfortunately, and several researchers, especially like Professor Barra at the Scripps, and they have applied this concept and into the DNA compatible chemical reaction development. Actually, in 2018, Professor Barra has just published this work. They could use this radical chemistry on DNA to develop this 1,4 addition for the try to form this sp3 bond formation. And 1 year later, they have using this resin compound basically, which could overcome the drawback for the DNA compatible reaction always requires water. Actually, here they can use the pure organic solvent to do some transformation. This really expanded the possibility for the OD reaction development. They have demonstrated they can do using this, they can do radical chemistry, they can do electrochemical reactions, and they can also do the lateral elimination. And this all these reactions have demonstrated the resin mechanism. organic chemistry is quite useful. We recently we applied this resin concept to some other reaction development. We did also found that the resin condition could have the better substrate scope compared with the traditional aqueous only reaction. So that at the same time, the scientists at Pfizer they have also come up with the photochemistry concept. The photochemistry, especially for this decarbonated cross-coupling reactions, actually they have demonstrated quite useful for the synthetic organic chemistry, also useful for the peptide substrate. And in 2019, we have demonstrated it could also work for the oligochemistry for the doing compatible conditions, and you see that their substance scope, you can find they are quite broad and it can be used for different types of amino acids, and they can be achieved in this sp2 coupling. And at the same time, Professor Gary Moran also demonstrated actually you can do this kind of like instead of also um, besides this one position, you can also just using this with the photocatalysis combined with nickel catalysis, you can also do this cross coupling for the sp3 and sp3 coupling, sp2 coupling partners. And this work collaborated with the GS2, which adequately demonstrated that all these types of normal chemistry here, basically they are also being compatible. And we are really excited to see these results, and my group actually sees this reaction is worked perfectly. And we are trying these conditions within the plate format for two reactions, and hopefully we can find the hit compound within this normal chemistry, right? So my group we are also interested in this type of photochemical conditions. So we use the teach IQ this type of scaffold as an example. We applied the both photo and the copper metal conditions, and actually we found that they can do especially at the C1 conditions, we can do all kinds of nucleophilic type of additions. We can add the nitro group, R10 group. We can also add the phenol ketones and also windows, so phosphate and the cyanide groups. All kinds of this type of the nucleophilic groups could be added with C1 position, and this could give you this diversified cycle. The scaffold currently we are working on the library design and synthesis based on this novel chemistry. And also the Wuxi chemistry leaded by the Dr. Shen Jiangpeng, they have also used this photo and this photo solutions. They have demonstrated two very nice examples about this type of application. And I think all of these examples has demonstrated that the photo conditions could be applied for the Delta very well. And with this, we recently published a new result with the substrate result is quite similar with the work by the scientists we have done, but instead of using this decarbonated activation, we can just use the simple this box-protected cyclic amines, and which we add differently. We just use to add the nucleotide. If you're effective, quite interesting. We can add it both as the very initiator, because we also find the side product basically can itself to have this type of additional product. But unfortunately, we can have this box protected mean as the major product, and by this way, and this could be used as a functional group. Because after the addition product, you can also do this before continuing then do the amine capture, and this is quite useful to synthesize the cyclic amine heterocycles as a fourth scaffold to make all kinds of this kind of the saturated heterocycle libraries. So with that, my group currently have already synthesized over 100 libraries, and the libraries will make it based on the privileged heterocycle scaffold. We try to develop the own DNA chemistry to synthesize this type of substitute heterocycles, which could really enlarge the diversity and and also for the making the combination of the power of the building block quite useful. And just as I mentioned, the majority of basically all the libraries will make just a half cycle and 3 cycle libraries, and we will control the library size basically. Church trying to make them just less than 100 minutes. And the next part, let's talk about the selection part. Actually, and this part, Professor Xiaojie recently published a very nice review in Campbell. And basically, currently we have the solution library and the bead-based library. We can also do the immobilized protein, in-solution protein, and emulsion protein, and also currently we can use the DEL to do the cell surface protein, and also you can do the selection inside the cell. And a lot of the research groups have contributed a lot to the advance of this field, and the Xiaojie's review basically summarizing this quite well. And especially recently, he has already demonstrated that you can use the photo cross-linking strategy to select the memory proteins, and they have demonstrated that they could achieve a very nice selection without basically in this strategy. And we just use my group just use already matured this selection method. We have done several selections for the protein target. This one is very simple. A very typical example. We using our own diagram board to screen this P300, and we can quickly to get 100 nanomole of as a hit compound. And we have also developed the covalent library selection processes, and we have tested for the 3CM Pro, and we can get a maximum range of the hit compound. We can also try some kinase such as BTK and JAK kinase. We can also get a very nice results. And here this just show one of the strategy we use is we just using different tech to put in the same building block. And this will just clearly show you that this three text for the one building block, and this building block is highly enriched, and we can have the hit compound just in the 60 nanomole small molecule. We are also interested to find actually for this protein target the only compound, and the DNA also we have show some like bonding affinity with the protein, and the only compound give you a little even lower with a little higher binding affinity compared with the off-DNA compound. And in the summary, and we in the last 2 years, actually, my group actually has already screened over 140 proteins, and we found around the 30 proteins, basically around 20%, they have very good full selection results. Basically, they could give you high quality, very clear SAR. But around another 50%, we found although they could give you useful information, but the SAR information is not enough. And basically, you couldn't do many medicinal chemical modifications just based on this cell interaction results. So and another 30% based on the cell, and maybe we found that this cell is not accurate for the selection for this type of protein target. So you roughly like my group basically we found around like totally 70% of protein targets there could give you the useful information, but we do think like just there itself try to give you high quality hits even to high quality need to give the hits to lead just there itself is not enough. So that's the thing we think about is how about whether we could integrate the artificial intelligence just with there, and whether we could with by this type of combinations you could generate like okay, make this technology more useful and make the hit identification, hit to lead optimization more effective. But the difference is this two technology definitely have the synergies. Basically, it's easy for you to think about basically they could generate a lot of data for the AI to build the model, and after you have the model, basically you can also use the model to predict more hits, which may be not obvious for the rest of their analysis. So we try to integrate these two technologies together. One of the examples we are quite interested in whether we could use using the AI for the reaction reagents, the building block filtering for the dialysis, whether we could use AI to build this type of model. Actually, this is one example of what at GSK we have done. This is a very specific thing, coupling reaction. We have validated over 10,000 amines, and actually finally we found only 20% of amines could be used in the laboratory structure, and 80% basically they are basically not very useful. So this is really a lot of waste. And if you have a model, basically instead of you are validating like of over 10,000, for example, you just need to validate 1,000. And using that model data, then you can do the prediction, and you can using this to find the building blocks which pass your model firstly. And this will save you a lot of money for the building block collections. And that's with this idea that we collaborate with Wuxi AppTech, and we have developed a new conditions for the pixel spectral reaction. And this one actually is quite unique in the Junction virus because they are acid promoted, and we have found this condition, and we basically validated over like 1,600 the aldehydes, and using this data, we have built a model, and to test this model, we actually bought the building blocks in the market, but they are outside of the original test, and which we found that the model actually works quite well. If you just do the random validation, you only have like 20% of the passing rate, but using the model, you could have close to 80%. So this not only demonstrates so the AI is basically useful for this type of building block filtering, but it also demonstrates that you can truly to use this model for the focus design, which is actually is the one of the main directions we think would have the huge impact in future for the hit to be the optimizations. And definitely after we developed this, we have used this developed this PS actually we have made a new library, and then based on this, and again, and this library actually we are counting the screening for different protein targets. We try to find some interesting hits based on this novel peptide spectral reaction. And another thing we think the AI and their integration could be useful is for the focus library design. Basically, is AI could guide you to design the novel, the specific their reactions based on the specific approaches. For example, if you have a fragment you identified by the different technology, either from there or just a fragment screening, and using this AI model to help you to design a novel their library. Basically, you can speed up your hit to lead this type of hit to lead optimization, and people give you the final results. And we have done a very simple application to use this concept. Basically, we use a model developed by my colleagues at my institution. Basically, they have developed the AI model for the BRD4 for the target to use this data published in the literature. And using this data we have made virtual lab reactions just based on the simple reactions we have. And by using this model, we screen this virtual library, and we take around 600 screen the virtual compounds. They have basically scores larger than 0.8, and with this the highest score is 1, and we just take this compound and we spit back to over a total is like 250 building blocks, and using this building blocks we buy them and just using them to make a new library, focus their libraries, and to basically try to confirm this how good this type of virtual screening for this type of books that we did. Actually, after the selection and the information we did found, we could get the 100 and more hits immediately from this type. Very simple. Total size is just like 10,000 average. And we think this type you can combine the virtual screening and this type with the building block filtering and also the focus library design to really help you to save the money for the huge libraries. If you just need to have a small library, you can achieve this type of the to lead optimization. But definitely, for the last case years, we already have an AI model for this protein target. But if you screen a novel target, definitely there is no data for you to do this type of modeling. So just differently, what you can think about is use for a new protein target. You can just do the cell screening first, and using the data generated by their screening, you can build up the model, and then in this model you can do many things. For example, you can just use this model to predict the compound the known from the commercial library, and this will be very interesting because actually Dell's libraries of chemical space are quite different from the known commercial available flow compounds, and this type of Dell and AI integration could help you to access different chemical space, and this concept actually recently has been demonstrated by the Navy AI, and they have last year they published in this paper, and they have demonstrated it's useful for 3 protein targets, and they could have around the hit rate at around 32, and for using the compound to have cut off at 30 micromole. And we have done the similar thing. And just using this, we think about this is we can have because we have screened a lot of protein targets, so we can use this as a demonstration. This we take the one of the protein targets that already have their data, and we build up the model, and then we try to see how good this is. And instead of you directly to after we build a model, instead of we directly to buy the commercial compounds to test, we try to see to test it. We can use the already known compounds to have a test. That's we got it because this target is known. Actually, there are a lot of the hit compounds and either like both positive and negative. They have already reported in the literature. The total like positive we have is we tested is around like over 1,000 positive, and we have around 700 negative, and so that's the result just based on the simple model the AI model and build up based on how their data. Actually, we found from like the true positive we found actually we can get around 22%, and the true negative we can get around 32%. Definitely the model is not perfect, and some of the true compounds the model is considered as a negative. Some of the true negative ones the model is considered as positive. But we did find this type of combination the model could give you some useful applications to combine this sales concept with the AI together to do the small molecule discovery. And we do think that actually this type of the data and the AI combination integration could give open some new doors for the small molecule discovery. Basically, you can now screen the campus space, not just the data, you can also screen the campus by the commercial libraries, also on some e-source or home demand sample libraries. And just the last couple minutes, just to try to introduce a company, Alpha Technology, which was built recently by myself and my colleagues and the SIMM, and we have built up this biotechnology. So we try to integrate the cell technology and AI technology together to speed up the small molecule discovery. And currently, our capabilities include from the target and hit and lead optimization, and also we could do basically try to do the global target identification, and also we could do from the hit to the lead, and also do the preclinical compound, preclinical compound optimization. And we have developed a series of AI-based drug discovery tools to speed up this process. And specifically for the AI and the AI and the cell combinations, when we have established this intelligent cell platform, and we have the very young and talented teams, and they have expertise from the AI, the DDD, from the Medica, and also from their own chemical reaction development and the synthesis, and we also have the established running. We have also there. We have also established the very A very good team. We could have all kinds of expertise together to speed up the discovery of the molecular structure using this type of integrated technology included there and the AI. And with that, I just want to last, I just regret to thank my group members and also the collaborators at the SIMM and also the several collaborators like the UCB and the GSK and the FSAC. We have done a lot of collaborations to really into the research work in their field. And with that, I'm very glad to answer some of the questions.
Thank you, Xiaojie, for your presentation. So please type in your questions in the questions. So yeah, there is I'm sorry if I miss it. Does DNA fragment and linker affect target binding in a screen assay? If yes, how is it possible to overcome it? So basically, the linker.
Sorry, I didn't catch that question.
So
could you repeat that?
Yeah, sure. The question is, does a DNA fragment and the linker affect binding in the screen assay?
No, actually, this has already demonstrated many times. Actually, the DNA will not. For some protein targets, it's likely DNA may have some impact. For example, like some of the transcriber factors, but I think for majority of the targets, it has been well documented. The DNA really have a little effect for the selection process.
Okay. So what do you think is the hardest technical part of working with DNA-encoded libraries?
I think it's something I didn't talk about this tutorial time is really how you analyze the data to find the true active compounds, because the Delta problem is different. You have a lot of like the false positive compounds, and especially if you have a larger library force, and you have a lot of low copy compounds, then you are not. If you don't have a good data analysis, if you didn't see a lot of the SAR correlations, then it's really hard for you to perform or you have the confidence that the positive compound you see is real, unless you spend a lot of chemical effort to make that compound. So I think this difference is very important to see. And another thing we struggle is basically is like you will have something. Sometimes you will have some interference. So this interference may come from like if your protein is not quite pure, and although you see the features, actually that's not your desired protein spider, it may bundle with something else, and sometimes you just don't know. Although the data is quite clear, them suggests you do have the bundle, but the bundle is not what you want. So this kind of thing is like to make the their work is better. You have the pure protein as much as possible, and also you could you could test that your selection method didn't work. So that's the, like if you have some positive compounds, then you design this type of selections, you could have better confidence about the selection that could make your success rate really high. Yeah, and you basically your hit conformation rate could be very good. Yeah.
Thank you. So by what criteria scientists choose reactions for DEL?
Oh yeah, I think that's very good question. The first thing is like that reaction must be being incredible, but the most important thing is you could really increase the diversity. And the diversity, I mean, is like basically you can have more building blocks to use used for the library synthesis. For example, we all know amines, aldehydes, and the acids are most abundant building blocks. And if you have direct reactions, you can use these type building blocks, and they are working quite well basically different type of the amino acids they can all use in this lab to be used for the scaffold synthesis or to make more diversity. That would be very great. So, yeah, but for this, I really love the you could do using the more building blocks as much as possible. That would be better.
Okay, thank you. Can we try iDEL technology with the DEL service such as OpenDEL?
Yeah. Oh, sure. Definitely, you can try the OpenDale, and there are several companies now currently provide the OpenDale. But the thing is like they also provide you a different selection method. They just need to pick the best one to fit the target you want to screen. Yeah.
Okay, thank you.
Mhm.
If talking about DNA-encoded libraries approach, and you want to compare it to HTS, to classical HTS, which one do you think will be more popular in the future?
Yeah, I think that's a very good question, but I think the currently so first is HTS because they although they have contain like 2 million compounds, but they do have the diversity chemical space and a lot and their chemical space is quite different compared with their chemical space. So I think they are quite complementary. But the HTS, the disadvantage is you need to spend a lot of effort, develop an assay, and also you need to spend time to complete the screening and the data. The other advantage is it's very quick to just screen the library. Currently, in my research group, basically after we got approaching from others, within one month we can provide them the selection results, and doing this they can be quickly to get the information. Actually, I would say later people will do their plus HTS, but maybe not a huge HTS, it's a small subset of HTS. Basically, you can using the information you generate from the delta, then you can screen the compound. Now it's like a focus set based on the information you have from the delta. So that's a little like the artificial intelligence I just mentioned. You can do the similar thing because they will give you the idea of what type of compounds maybe have interaction with your desired protein, and you can combine it both. So I don't think like in the future will be, oh, I only do there, I don't do HTS, or I only do HTS, I don't do there. I think you can do this combination.
Oh,
Yeah.
thank you.
So,
Um, yeah, the question is a kind of obvious question. How big
mm,
is the biggest DEL you know about?
how big it means the library size?
Yes.
Oh, so I personally make a library with is 2,000 billion, like 2 trillion compounds. I personally make. I collaborate with one of my colleagues, and we made a 4-cycle library. And we have a space size 2,000, 1,000, 1,000, and another is like 1,000. We make a 2 trillion library, and we use this 2 trillion library in the screening. And for certain protein types, yes, you can get a hit, but in majority of the time, you couldn't get enough information, and then this library is too big. Majority of the time, you just get really low copies. Yeah,
Okay.
right. Yes, if you want to have a big library like a trillion library, yes, you can make it just with one library.
Okay. Yeah. Thanks. I think we don't have any other questions. So with that, I would like to thank you, Xiaojie, for a really nice presentation. For your, thank you everyone for attending webinar. And with that, I would like to close the event. So have a good one. Bye.
Thank you. Bye bye.